The 1st of May, 1960, 05, 36 inches the morning. The sky above Peshawar is clear and cold at altitude. Gary Powers sits inside the narrow cockpit of a Lockheed U-2, climbing northeast into Soviet airspace. He departed from Peshawar Air Station in Pakistan before dawn. His destination is Bodø Air Base in Norway. His mission is photographic reconnaissance. Below, Soviet military installations stretch across the steppe. He will never reach Norway. Near Sverdlovsk, an SA-2 surface-to-air missile finds the U-2 at altitude. The airframe loses structural integrity. Powers ejects, descends by parachute into Soviet territory, and is taken into custody. Within days, the incident becomes a diplomatic crisis that will hold both governments at a standstill for weeks. President Eisenhower is cornered. Khrushchev takes the podium in Moscow and displays photographs of the wreckage to the world. Inside Washington, the more consequential response happens quietly away from the cameras. The CIA already understood the implications. The U-2 had always been visible to Soviet radar. Intelligence analysts had assumed incorrectly that Soviet missiles could not reach the aircraft's operating altitude. Powers proved that assumption wrong. Soviet air defense had matured faster than anticipated. Their radar networks were broader, their missile systems more capable. The U-2 was finished as a deep penetration reconnaissance platform. What was needed now was something fundamentally different, an aircraft that flew higher than any missile could reach, faster than any interceptor could follow. With a radar cross-section small enough to complicate targeting solutions, the requirement was extraordinary. So was the response. At the rear of Lockheed's Burbank facility, behind unmarked doors, sat a division called Skunk Works. Its director was Clarence Kelly Johnson, the same engineer who had designed the U-2. Johnson ran the operation against the grain of post-war American defense contracting. Small teams, direct engineering decisions, no bureaucracy between design and production floor. The engineers who drew the plans also solved the manufacturing problems. Johnson's team began work on what would become the A-12, a single-seat reconnaissance aircraft developed under the CIA's Oxcart program. It made its first flight on the 26th of April, 1962, above the Nevada desert at Groom Lake. The performance data was exceptional, but the Air Force required more. A second crew position, a larger reconnaissance bay, extended fuel capacity. The A-12 became the starting point for an entirely new design. On the 22nd of December 1964, the SR-71 prototype lifted off the runway at Palmdale, California, for the first time. On that first flight alone, it broke the sound barrier and climbed to 13,700 meters. By January 1966, operational aircraft were being delivered to Strategic Air Command. 32 SR-71s would be produced in total. The central engineering challenge of the SR-71 was heat. At Mach 3, sustained friction against the atmosphere raises airframe surface temperatures above 300 degrees Celsius. At the wingtips and leading edges, higher still, aluminum softens at that temperature. Steel holds its shape but adds prohibitive weight. The solution was titanium. 85% of the SR-71's airframe structure is titanium alloy, the remainder advanced composites. But in the early 1960s, the Soviet Union was the world's primary exporter of titanium ore. The irony was complete. The CIA needed Soviet raw material to build the aircraft designed to spy on the Soviet Union. Front companies were established across multiple countries, orders placed under cover stories, golf club manufacturing, agricultural equipment, industrial tooling. The rutile ore arrived at Lockheed's facility. The Soviets never learned its destination. Working the metal was its own discipline. Titanium is highly sensitive to contamination during fabrication. Lockheed engineers developed new welding procedures, new heat treatment protocols, and new tooling from scratch. Nothing in existing commercial aviation manufacturing applied at this scale. Ben Rich, a thermodynamics engineer at Skunk Works, who had worked closely on the inlet and exhaust systems, later described the situation plainly. The Russians had unknowingly helped build the aircraft sent to photograph their own country. The aircraft's black ferrite coating served two purposes simultaneously. The iron ferrite particles absorbed radar energy, reducing the aircraft's radar cross-section. The same surface dissipated accumulated heat outward through thermal radiation. The SR-71's geometry reinforced this, further the smooth blend between fuselage and wing, the chine edges running the full length of the nose section, the angled engine nacelle positioning. Each feature reduced radar reflection. The Blackbird's appearance was the result of engineering necessity, not aesthetic choice. At the core of the SR-71 sit two Pratt and Whitney J58 engines. Each produces 32,500 pounds of thrust at full afterburner. Their operating principle has no equivalent in standard aviation engineering. Below Mach 2, the J58 functions as a conventional afterburning turbojet. Above Mach 2, bypass valves open, compressed air routes around the rear compressor stages and flows directly into the afterburner. The engine shifts into a turboramjet configuration. This mode transition is what sustains cruise above Mach 3. At Mach 3.2, the thrust breakdown tells the real story. The air inlet spike produces 54% of total thrust. The expanding exhaust nozzle at the rear accounts for 29%. The engine core itself generates only 17%. At operating speed, the J58 functions primarily as a heater inside a mechanical air trap, stabilizing a captured shockwave around itself. Starting the engines requires external assistance. Dedicated start carts, each running two large V8 engines coupled together, spin the J58 rotor shaft up to 4,500 revolutions per minute before ignition. When the engines light, the heat and noise radiating outward across the ramp are tangible at considerable distance. The SR-71 burns JP-7, a fuel formulated specifically for this aircraft. Its evaporation rate is extremely low. A standard open flame cannot ignite it. The aircraft carries more than 46,000 liters. At full afterburner, consumption runs approximately 30,000 liters per hour. Before reaching the engines, JP-7 circulates through the airframe, cooling hydraulic fluid, engine oil, and the crew cabin. The fuel system is the aircraft's primary thermal management circuit. On the ground before departure, fuel pools form beneath the aircraft on the ramp. The SR-71's tanks have no rubber bladders. The titanium outer skin is the tank wall directly. Cold metal contracts, leaving small gaps in the structure. As the aircraft accelerates and the airframe heats to operating temperature, the titanium expands and the gaps seal. Every mission therefore begins with an aerial refueling shortly after takeoff, conducted by specially modified KC-135Q tankers, once the structure has stabilized. The crew suits up hours before the aircraft does. At 25,000 meters, unpressurized air cannot sustain human life. The flight suits are functionally close to what early astronauts wore full-pressure garments, not flight clothing. The SR-71 flew from bases in the United Kingdom, Okinawa, and the continental United States. Its missions covered the perimeter of Soviet airspace, the coastlines of North Korea, the skies above Vietnam, and the Middle East. The aircraft never entered Warsaw Pact or Chinese airspace directly. Its side-looking sensor array could survey 260,000 square kilometers of territory per hour from cruise altitude. An astro-inertial navigation system tracked star positions in broad daylight to maintain positional accuracy across featureless terrain. On Okinawa, local residents gave the aircraft a name, Habu, a venomous pit viper native to the islands. Long, dark, and fast, the name settled quietly into use among the crews themselves. Over its operational career, surface-to-air missiles were fired at SR, SR-71S. On numerous occasions, the count of successful intercepts is 0. When a threat warning reached the cockpit, the crew advanced the throttles and climbed. The missile's kinetic energy ran out before the aircraft came within its lethal radius. On the 28th of July, 1976, 2 records were established officially. The SR-71 reached 3,529.56 kilometers per hour, the absolute speed record for an air-breathing powered aircraft. On the same day, it climbed to 25,929 meters, the absolute sustained altitude record. Neither has been broken in the 50 years since. On the 1st of September 1974, an SR-71 flew from New York to London in 1 hour, 54 minutes, and 56 seconds. On the 6th of March 1990, its retirement flight covered the distance from Los Angeles to Washington in 1 hour, 4 minutes, and 20 seconds, averaging 3,418 kilometers per hour. Upon landing, the aircraft was transferred directly to the Smithsonian National Air and Space Museum. The Air Force retired the SR-71 inches 1,990. Brief operational revivals followed through the decade as the debate over satellite versus airborne reconnaissance continued without resolution. On the 9th of October, 1999, the last SR-71 departed Edwards Air Force Base for the final time. 20 of the 32 aircraft now stand in museum collections. The titanium airframes remain intact. The black ferrite coating has faded in places. Outside the Smithsonian's Udvar-Hazy Center, one SR-71 sits low on its display mount, engines cold, fuel lines dry, cockpit sealed. The aircraft that once covered a kilometer every second now does not move at all. No one has built anything faster since.